Hey, hi. Today we're going to look at the application of the kinetic theory formula in the verification of the ideal gas laws. We shall be verifying Charles' law, Boyle's law. We shall go ahead and look at Dalton's law of partial pressure, and also we shall look at Avogadro's, and if time allows, we shall also look at the Graham's law of diffusion. So we want to start with the Boyle's law. Before we verify Boyle's law, we need to know what does Boyle's law state. In brief, Boyle's law tells us that the pressure of a fixed mass of a gas at a constant temperature is inversely proportional to its volume. Okay? Now, we need that information because it will guide us in whatever we are going to look at. Now, when we talk about fixed mass of a gas, it means that the mass that is contained in a vessel does not escape. That means that the total number of molecules remains constant. So if the vessel has got a total of n identical molecules, each of mass m, then we can be in position to get the mass of the gas in the vessel, which will be the mass per molecule times the total number of molecules. In that way, if we divided that mass by the volume of the container which the gas occupies, we end up with its density. Now, we are looking for this density because when you look at the kinetic theory formula, a third rho c squared bar, there is this concept of density, and this density does not feature anywhere when we are dealing with Boyle's law. So we are looking for this density so that we can substitute it here. Then we find a way of simplifying whatever we are doing so that we match the concept of Boyle's law. So if we brought the mass that we have from the previous presentation, we do get something that you see on your screen, and that one simplifies to that equation that we are at that particular moment. Now, from this point, there are two ways to go about this verification. I'm going to present one method or approach in Boyle's law, then I will present the other second method in Charles' law, for which case you can also apply the one I'm going to present here on Boyle's for Charles, and also try to apply the one I will have presented for Charles to the Boyles. Now, at this point, we're going to produce the concept of kinetic energy. Now, if you remember in our discussion, we said that kinetic energy, the average kinetic energy of molecules of an ideal gas is given by that formula. Okay? And we know that eventually we discover that this kinetic energy is directly proportional to the absolute temperature. So in the event that this temperature is kept constant, then the kinetic energy is also constant. Okay, so that is the concept we want to introduce. So if we introduced that, that would mean that wherever we have this expression of a half mc squared bar will be a constant. After all, Boyle's law tells us that the temperature must be kept constant. So you can see that I've introduced two outside. That one has to be counterbalanced with a half. And now what we have in this bracket is exactly what I was talking about here. Okay, so if I want to get away of, I wanted to wrap that one, but I think we can still see it. That particular quantity we have mentioned from our discussion is proportional to the temperature, which we have said in one way or the other will be a constant. So what does that one tell us now? It tells us that if this is constant, since the temperature is constant, the total number of molecules, since the mass of the gas is fixed in the container, we said will also be constant. And that literally means that even 2 over 3 is a constant. So the whole of the right-hand side, therefore, is a constant. So it therefore means that PV is equal to constant. And if you remember from your discussions, that one is actually Boyle's law. And in that way, we shall have verified Boyle's law using the kinetic theory formula. Are we together, guys? That is basically how we go about this discussion. I hope this serves you well. If you have any queries, please raise. You can directly inbox me. Thank you.